Right, here is a video looking at this question on electromagnetic waves. We're going to start with a few quick descriptions, and then we're going to get down to the nitty-gritty of the maths. So the first one says, what do you understand by electromagnetic wave? Well, if we, a nice little sketch might be appropriate here. This, electromagnetic waves are an oscillation in the electric field, and with respect to time, and also, if I was to draw another axis there, the magnetic field with respect to time. And those are mutually perpendicular. It's actually a wonderful diagram I've drawn there. At every point, they're perpendicular to each other, and they have the same frequencies. The magnetic and the electric fields have the same frequencies, and they don't require a medium to travel through, so they can travel through a vacuum. Good, but major points there. It's an electric field. It's an oscillation electric field and a magnetic field, which they have the same frequency, but they're traveling at right angles to each other and go through a vacuum. Fantastic. That's a quick one, but I want to get on to the nitty-gritty here. Now we have the intensity of the wave is the average energy passing per unit time per unit area. So what we can say is I is going to be an energy over a distance squared per second, if you like. And it says here that it's asking, and it's showing a simple dipole, and that's transmitting, and you're looking at the intensity which gets to a point Q, so IQ. And it's asking you, first of all, to work out the base units of Y naught. So in other words, what I'd probably do here first is I'd rearrange and say IQ 2R squared divided by E naught C sine squared theta. And instantly I'd say to myself, if I'm doing this as base units, I can say that's IQ R squared. I can get rid of all these constants, wonderful constants. E naught C, and that's Y naught squared. So I know what R squared is. I know what C. I need to work out what E naught, and I, Q, I've just worked out up here. What is E naught? Well, we can work out E naught. Let me use this space actually whilst I'm using it. We can say that I know from Coulomb's law that F is 1 over 4 pi E naught, Q1, Q2 over R squared. So E naught is going to be Q1, Q2 over force R squared. Of course, we know that Q is I times T, so we could say this is amps times seconds, but of course I've got two lots of that squared divided by newtons, but newtons, force is a mass times an acceleration, so it's probably better to write that as kilogram meters per second squared by meters squared. So the base unit of E naught is going to be amp squared second squared over kilogram meters cubed seconds to the minus 2. Okay, now I need to plug all these together. So I've got my E naught, I've got I, Q, I've got R, C is a speed, of course, and that gives me Y naught. So let me bolt that all into that. Y naught squared equals what I've just got here, amp squared second squared over kilogram meters cubed seconds to the minus 2. Multiplied by meters squared, because I've got that on the top. And then on the bottom, I've got meters per second. So I multiply by the inverse, that's seconds over meters. And let me invert, oh goodness, that was E naught. So let me invert that one, because that's the bottom. Sorry for doing it the wrong order. And here I have energy work done, which is force times distance, and force we know is a kilogram meters per second squared by meters. So two lots of meters fall out, giving me, so that cancels with that, seconds gives me kilogram seconds to the minus 3. So kilogram seconds to the minus 3. Right, this is starting to get complicated, but y naught gives us, let me invert that straight away, kilogram meters cubed seconds to the minus 2 meters squared seconds over meters by kilograms seconds to the minus 3, and divide it all by amps squared seconds squared. And that leaves me with, I'm just going to reference the work I did before just to make absolutely sure for you here. That gives me, we're looking at yes, so let's take a look at this. So the kilograms, I'm just wondering where to write this now. Let me roll it onto another page here. We've got kilograms squared, because that's that and that one put together. We've got seconds, so that one at the bottom, and I've got seconds there and there, so that's seconds to the 4, seconds to the minus 7, minus 6. I then have meters cancels that one, but that's with 5, so that would be 4. I've got amps to the minus 2. So I've got kilograms, amps, meters. Perfect. And that gives me y naught squared. So y naught is going to be kilograms, seconds to the minus 3, meters squared, amp per amp. Actually, that is the unit for potential difference. Because if I were to rush through this in another way, I could say to myself that E naught is farads per meter. And so therefore, y naught squared is going to be IQ R squared over E naught C. Oops. And I naught is going to be equal to charge squared. Sorry, what are we talking about? I naught is just, yeah. If I had more time, we could work that through and it would come out as volts. No, do you know what? We're going to do it. All right, here we go then. Just to convince you that this does come out to be a volt. But Google that and you'll notice that it does come out to be a volt. So here we go again. Let's go. I Q R squared over E naught C is Y naught squared. IQ was given before. Work done. So we had a, I'm going to be a little bolder here and not derive these so far down. So it's going to be work, it's going to be joules per meters squared seconds, because it's the work done, it's the intensity, so that's the power over the squares, multiplied by meter squared, divided by farads over meter, multiplied by meters per second. So those drop out, so leaving us with joules per second over farads per second. Those drop out neatly, leaving me with joules per farad. You know that Q is CV, so C obviously is Q over V. Voltage is the number of joules per coulomb. So if I take that, so farads are joules per coulomb, so it gives me joules over joules by Q squared, Y naught squared. They drop out, so Y naught, sorry, Q volts. So therefore Y naught equals, whoops, so Y naught equals volt. Okay, took a long time on that one, but it's probably worth seeing from both sides. Next bit asks for us to look at this situation here from the dipole and then work out the total power radiated of P naught and use that to work out what IQ is. So we're looking for the total power, we're looking for the whole of that surface area. And how are we going to get there? It gives us a wonderful integral. And so we, with respect to theta, so we know we're going to have to do something with respect to theta this way here. It also gives us a 0 to pi, so it's only looking for us to move from one point to the next point and integrate up over there. But we're looking to find the surface area from this. So what I suggest we do is work out P naught. The total power is going to be the intensity at Q multiplied by the area. This being an integral here suggests that actually we're looking for a small area, an elemental area, and then we're integrating it up from 0 to pi, because that's the hint we're given. So how do we construct this in order to allow that to happen? Well, what I think we ought to do is we ought to imagine this as a series of rings getting ever smaller, ever larger as we go round, and smaller as we come to the midpoint, and then smaller as we go back. The projection at the midpoint is r, but at any point subsequent to that, it's going to be r sine theta. Good. That's just giving us a very small element, but what we're looking for is this very small area that we can then multiply up. So this bit here is given to us by r d theta. It's just the small angle multiplied by the radius, which is here r d theta. So therefore this elemental area dA is going to be the circumference of that ring, which is 2 pi r sine theta, multiplied by that small width. And this we then have the chance of integrating from this point all the way round to that point. Let me just write down the entire equation then. So I need to substitute this here into there, and obviously this I have already there, so I put them all together. So P naught is going to be the integral of, let's write this all down, we have E naught C y naught squared sine squared theta over 2r squared multiplied by 2 pi r sine theta r d theta between 0 and pi. Luckily, these cancel out with that. That disappears with this, and therefore I'm left with the integral from 0 to pi of all the constants sine cubed theta d theta, which gives me a wonderful result, 4 over 3 E naught C y naught squared pi. That is not yet in this format. This is given in P. This is given in y naught. So what I'll do is I'll come back to here and work out what y naught squared is equal to, which is IQ 2r squared So it's I naught 2r squared divided by the remainder, which is E naught C sine squared theta. And I'm going to use that and substitute it into the bottom down here, which will give me, let's just hold that. Can you see both of those in shot? Nearly. I'm going to write them out again on this new bit of paper. We have y naught squared is IQ 2r squared E naught C sine squared theta, and we're going to bolt that into 4 over 3 E naught C y naught squared pi, giving us 4 over 3 E naught C IQ 2r squared pi divided by E naught C sine squared theta. And now you can see these are starting to drop out nicely, giving us 8 IQ 8iq, p naught of course, 8iq r squared over 3 sine squared theta. Is that right? 3 sine squared theta I naught. And I've got a pi on the top there too. Okay, now quick rearrangement. Therefore, IQ gives us 3 p naught sine squared theta over 8 pi r squared. QED. That's what it was looking for there. Okay, not out of the woods, but that's cool. It's quite a useful little equation there. Okay, meteorological balloon rises up, and of course we have a projection of what intensity hits the ground. Now that is pretty much the same as what we've got here if you imagine that to be upside down. So if we put the antenna at the top, then when we inverted that, Q's at the bottom, theta's at the top, Q's at the bottom, then we can use the same identity that we used before on the previous page. So it says, suppose the dipole is a fixed position, find the expression of the intensity of the signal received as a function of theta. Okay, so here is our height. That is D. I'll call this one R. And that leaves us with R is D over cos theta, over cos phi. D, so we're relating R to D. We also know that I is equal to 3 p naught sine squared theta over 8 pi, and the R is of course D over cos phi squared, which gives us a lovely identity of p naught cos squared phi over 8 pi d squared. This, however, here is exactly, because we've inverted it all the way around, the sine squared, you can effectively say that sine of theta is the same as cos of phi. Just make sure you get that bit. There is the antenna, this is the ground. You've got, you would have in effect here, phi. So therefore, cos of phi is the same as sine of theta. So therefore, this would of course therefore be cos squared phi as well, which gives us 3 p naught cos to the 4 phi 8 pi d squared. Okay, now it gets a bit trickier here. If the dipole remains vertical, the signal becomes too weak to be detected at ground station when it has a height of. So here's our dipole. When we have D, and at the point of 2D, that is the point that it is too weak. So that's number 1, this is number 2. That's the point of too weak. So therefore, what angle is that? Theta. Well, we know that, tan phi, we know that's going to be 2d over d, which gives us 2. So phi is going to be something like tan to the minus 1 of 2, which is 63.43. So then cos to the 4 of phi gives us 0.04. So there's our condition. So I minimum is going to be 3 p naught times 0.04 over 8 pi d squared. Now, we've got the next setup, which says that they're going to rotate the dipole so it's always perpendicular to the ground. HD, now again, phi. So this is rotating. So if it's rotating, it's always perpendicular. We have the function is the trigonometric function is always going to equal 1. So therefore, that leaves us with saying that 3p01 over 8 pi r squared is going to be equal to the minimum, which was previously r, of course, we need to change to be d and h squared. So we have h squared plus d squared. And that must be equal to the minimum, which was 3p0 times 0.04 with 8 pi d squared. All we now need to do is resolve this. So we get rid of those. That's a good start point. We get rid of those. And that leaves us with, I'm just going to draw it, it's going to be a bit small, but I'll draw it all into here. That leaves us with, if I'm right, 0.04 h squared plus d squared gives me d squared. 0.04 h squared is 0.96 d squared, so therefore h is 4.9 d, approximately 5 times as high, and that's what it's asking for. To what height can the balloon be tracked if the dipole orientation is continually adjusted to give maximum intensity? The answer is 4.9 d. Good, nice little question. I hope that makes sense.